Good night, Professor. I'm Wilfredo Acevedo, the owner of Solar System. I'm going to present the phase C1. This is the outline. Um, in this part, we talk about the interface diagram, the detail analysis, the design specification on drawings, the verification on project plan. And now we have the problem statement. That is the interface diagram where we will be looking at the problem statement and what is going to be solved. That we have the consumption of the office, the actual consumption, and the charge analysis of the office. And now we have the new charge analysis of the office and the RSpeak analysis of the in 1 year of the Calle Peru. That is the ubication of the office, and the average that is $5.6 hours. Sorry, 5.6 hours peak. And now we have the analysis to calculate how many PV panels the office needed. That is, we have the energy provided by panel, the sun's hours peak, the maximum power for panel, the nominal voltage, and the maximum voltage for the panel. And here in the final analysis, we have the 21 panels according to the electrical characteristic of the monocrystalline PV panel. The specification of the strings are 3 strings of 7 PV will be worked for this design to complete the voltage balance per string. And the 3 strings must have the same voltage to complete the specification of the inverter. And this is the analysis of the voltage balance for strings, where we have the number of panels, the PV watts, open circuit voltage, that is a specification of the PV panels of this project, the short circuit current per module, the total current per string, the amount of strings, the total voltage per string, and the total power in the array, and finally the total current in parallel. And this is the diagram of the string. The 7 PV panels in series. The capacity of the each panel has 410 watts, where in the series analysis the total voltage of this array, that are 7 panels per 490.6 voltage, that is the voltage of each panel. According to the law of Ohms, the series voltage is added, the total current are the same, applying the Ohms equation, and the total power in the array are the 7 panels per the capacity of the panel, that is 2,807 watts, and the total power in the strings are the 3 strings per the total power, that is 8,610 watts, and the maximum voltage in the array are 347 voltage, and the maximum voltage capacity of the hybrid inverter are 500 voltage. The strings array is on the margin, and this is the specification of this solar inverter. And now we have these 3 strings of the 7 panels in parallel. that we have the capacity of the panel, and that 1 PV represents the 7 PV in series, and 3 in parallel, where we have the total voltage in parallel that is the same. Applying the law of ohms, the total current is added, that is for the 3 strings in parallel, for the 10.7 amperes, that is the total current in parallel, are 32.28 ampere. The total voltage in series is the 347 voltage, and the final array, that is the 7 panels in series and 3 PV panels in parallel. We have the final string with the 3 strings and 7 panels in series and 3 panels in parallel. And the part B of this problem is determine the hybrid inverter capacity, that the capacity of the inverter is determined with the immediate demand of the system. In our case, the power required at the moment of 7,838 watts, and the capacity available for the manufacturer is the 8,000 watts. With the design system meets all specifications of a hybrid inverter. And this is the specification: the max allowed PV power, the max DC voltage, and the AC outputs connections, and the battery specification, and the general specification, that is the weight, dimensions, and the all of the specification. In the part C, we're gonna determine the power capacity of the lithium battery and the amperes hours needed. To determine the battery, we have to make first the charge analysis for non-critical loads, and the non-critical loads are what the customer wants the battery bank to keep on AEE is lost, and there is not enough sun, and this is the new charge analysis for determining how the battery. In the power capacity of the bank lithium, the power required by the battery bank is established with the watts hours consumed by the non-critical loads in the office. The non-critical office of the office are 8,752 kilowatts per hour, and the lithium manufacturer has available a power of 10.24 kilowatts hour. And this is the details of the battery, the specification of Fortress LFP10 lithium battery. To determine the ampere hours of the office, we have to make this analysis, that is the total charge, the consumption of the all devices, the day of autonomy, that is the day that will the system work only with the battery. If AEE falls, the nominal voltage, the battery bank discharge, the efficiency of converting for chemical energy to electrical energy, and the efficiency of the hybrid inverter. And this is the analysis, and the current capacity of the battery as a 198 ampere hours. And we have an important note: the calculated amperes hour capacity complies with the amperes hour of the specification of the manufacturer, that is in the March or in the margin of the specifications. And in this table, we see the tilt angle, where we can see the, that the that out latitude is 18 degrees. It will remain at the angle, and in this part we're using the theoretical equation. And this we have this equation to determine the angle of inclination of the cells, that is approximately 16 degrees. We have the coordinates of the office, that is Calle Peru. Latitude of the office is 18.14 degrees. In the analysis, according to the table above, if the latitude is between 15 to 25 degrees, the degrees of inclination of the panel will be the same of the latitude, and the angle of inclination of the photovoltaic panels will be between approximately 16 to 18 degrees, which is within the margin. And this part, we have the different loads analysis with the old AC system versus the new VDF system. And now we have the analysis of cost of production of the system, that we see the excess of energy of the system is what PREPA will be buying, where the excess energy is the power of the inverter minus the power of the office. Then we have the given that the office power, the inverter power, and the calculation is the inverter power minus the office power, that is 0.62 kilowatts. This is the energy in a day. The days of operations of the office are 5 days. The exact system energy, that's inverter power minus the office power. The final excess system power in the months are 25.92 kilowatts hour. That is the PREPA going to buy. This is the excess of energy of the system. And according to the law number 114, established the 75% of the surplus energy will be purchased by AEE at 10 cents per kilowatt, and the 75% of $25.92 are kilowatts hour are 19.44, and the 19.44 per 10 cents are $1.1. This is the amount of PREPA will be the excess energy sold. And this is we have the office consumption charge, where the excess energy for the fridge is the new consumption energy. And the excess of the fridge is not covered by the 8 hours of the system, will be the new consumption. The office operate 8 hours 5 days of the week. The fridge consumes 24 hours of the 5 days. The excess of 8 hours that the refrigerator we multiply by its power to determine when it's more excess. And the analysis, we have the excess hour of the fridge that is the fridge hours minus the office hours. The excess power is the mini fridge per excess hour of the fridge, and the excess of energy for the days. Now, is the excess power per 5 days, and the final excess of energy in the months are the excess power fridge per 4 weeks. That is the month. An important note of this analysis: the 15.36 kilowatts hour is the new consumption of the system monthly with the new PV system design. And now we have the comparison of the energy cost, that the old costs are $295 versus the new consumption, that is $7.31 minus the 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 $1.919 that Prepack is going to buy paid for the excess energy of the inverter, that the new consumption energy are $5.36. The consumption in the year are $3,500. The new consumption consumed in 1 year is $64, and the savings in 1 year are the all consumption means the new consumption, that is the savings in 1 year are 3,485 dollars, and the new and the investment recovery and the cost of the system divides for the savings in 1 year, and the investment of the photovoltaic system will be recovered approximately in 5 years. In the right, we have this graph, and this graph we see the enormous difference in monthly cost of the office. We have that that the $5.36 are the new consumption of energy. That is an enormous savings for the customer. And now we have the detail, and in this detail analysis we have the Wari analysis. We have this Wari analysis using the National Electric Safety Code, using the Cooper, specifying the Cooper, and the system being identified and grouped as required by NEC Art 6690 to find the size of the cables. We will use this article with the copper material, and that resists a maximum of 1990 Celsius degrees. And this is the all of the analysis to determine what cables need the system. And now we have the design specification and drawings of the project. We have the title, the site plan existing utilities, the new electrical components, the one-line diagram for 21 panels, and the conductor sizing diagram and wiring specification for 21 panel design. And this is the existing utility. We have the 16 primary line and the secondary line of to 240 voltage on the transformer, existing meter, main breaker of 100 amperes, the parking lot that is here, the roof usable for PV panels, the existing air conditioning system that we move for the new system BRF, and this is the street of the office and existing panel distribution. And we have the new electrical components. And in the left, we presenting the 21 panels oriented to the north. And we have the 3 strings of 7 panels. And they have a belter, solar arc, 8 kilowatts. And the one bank of battery, Fortress lithium battery, non-critical load panel, and existing critical edge load panel. Okay, that is in this side. And this is the connection of the system. We have the 7 panels in 3 strings, the junction box, the rapid shutdown, the combiner box, the inverter, the backup battery, and the general duty non-fusible safety switch disconnect, and the automatic disconnect for non-critical loads is and the non-critical load panel, the existing main breaker, and existing meter, and utility prep. And we have the wiring nodes and the conductor sizing calculations with the new system that is the array to the combiner box to the inverter to critical loads, and the existing wiring, and the drawings for the devices. That is the monocrystalline PV panel, the 410 watts, the Fortress lithium, 10.24 kilowatts hours, the solar arc hybrid inverters in kilowatt, and this is the verification show produce 7.8 kilowatts, performance 8 kilowatts, in completing phase C1, and competence yes, most durable equipment in phase B, most storage energy C1, must reduce of cost of energy in C1, and must have the proper orientation to receive all solar energy, phase B. The initial budget establishes that is the $28,000 versus the new cost of the system, $70,427. And the project plan, we presenting C2 in April 17. And that is all. Thank you, Professor, for your attention.